And yeah, I think the stage.
Thank you very much. Okay, everyone. Nice to meet you. My name is In-ho Jung. In-ho Young, Jung, Jung, same. Typically, when I come to the Europe and in the airport, sometime people checking the client, in the airport, and say, Mr. Young, Mr. Jung, and never actually say Mr. Jung. My name is actually the Jung. It's okay, no problem. I'm very used to it. So today, I'm going to talk about thermodynamics. I know everyone knows thermodynamics, but when you turn around, everyone don't know the thermodynamics as well. Yeah, I believe so. Everyone knows first, second, third law of thermodynamics, but when you go to the more, Gibbs energy, reaction, activity, and now if you really go to the phase diagram and then complex, the phase analysis, then you start to like confusing about what I'm doing. And so what I want to show you today is give you the short review about your fundamental thermodynamics. Thermodynamics 101 again, engineering thermodynamics. And then I'll bring you to the little bit of the computational thermodynamics and a lot of people using FactSage. And by the way, I'm the one of the developer of FactSage. So I'll show you a little bit about that. And then I'll show you a lot of the different examples about how to use this kind of the software to understanding the degradation of the refractory, not only by slag, phase transformation, and then by the metals, and also by the gas. And this is probably most of the application we need to understand the refractory degradation. That's what I want to show you in the next about 40 minutes. And then if everyone happy, then I'll take a group photo together before we take a group photo outside for my Facebook memory. Okay, so 3 laws of thermodynamics. Everyone knows this one, yeah? First, second, third law of thermodynamics. But believe it or not, if you just hide the answer, some of you say, what was third law of thermodynamics? But what I say, none of this one is very important. To say frankly, when you go to the real refractory, understanding. So forget about it. So let's just move. The important thing is how to understand the Gibbs energy of the pure species. Single species, stoichiometric species, compared to the reaction and then solution. That's actually the essence of the thermodynamics you need to understand the degradation of the refractory. So now this is the Gibbs energy for the pure species. When I say pure, it's stoichiometric. It's not like solution species like FCC, BCC, or liquid slag, So for example, CaO or MgO or Al2O3 or pure oxygen Gibbs energy is all expressed in this way. G equal to H minus Ts. Everyone knows their terms. I don't want to explain. And here, especially we have the G naught, H naught, and S naught. This is classical kind of symbol we are using to representing that this is the pure standard material species. Okay, so you have to know this. Sometimes this knot is disappearing. It means we are not talking about any more pure species. Okay. So H enthalpy is start from enthalpy 298. Standard enthalpy of formation we call plus integral of CPDT, and S298 plus integral CP over the TDT. So everyone knows about this one. But a lot of people computing why H containing delta H and S containing just S298. Because when the classical thermodynamic was developed, we didn't have quantum mechanics. So we didn't know the enthalpy, absolute enthalpy value for the materials. So that's why these smart actual people, when they start develop this kind of thermodynamics Gibbs energy function, they say, do we have to really know the absolute enthalpy? Because we want to know the chemical reaction compared to the one to the other one, energy difference. So we need relative energy difference. So we don't need the absolute value. If you can know absolute value, it's nice. But even without the absolute value, if you know the relative value based on something, then we can use that to quantify which one have the low energy state than the other one. Yeah. So that's what we did. So that's why we say that delta H298, H is starting from delta H298, which called the standard enthalpy of formation from the old elemental species we can find out in periodic table, which is stable at room temperature and the room pressure condition, which we can easily obtain. So they mixed, for example, aluminum, oxygen together to make alumina. And during that, you can measure the enthalpy change. And that enthalpy change is, we call it standard enthalpy of formation. That's the delta H298 Kelvin. Okay, so you can assume that then pure aluminum equal to 0, pure oxygen equal to 0, and then Al2O3 have that reaction enthalpy. That's how we define. And S, because of third law of thermodynamics, we know the absolute S at 0 degree Kelvin for the pure crystalline material is 0. So by the integration of CP, we can actually get the S298 absolute value. Okay, so by integrating all this equation, we can define the Gibbs energy of the pure material like Al2O3. Okay. Now, but we want to make something. So it means we require always chemical reaction. So now let's start with the chemical reaction. So you have A plus B become AB, kind of chemical reaction. Is this chemical reaction going to the forward or not forward? Yeah, that's what we want to actually understand. And so Gibbs energy of reaction, okay, here you have the two terminology, G naught of delta G naught of reaction. This means this is Gibbs energy change of the pure AB minus pure A minus pure B. That's what this means. But when we say globally, when you say, okay, whether this chemical reaction going to the forward reaction or backward reaction, you have to always look at delta G of reaction, okay? Because later I'll show you that your component, reactant or product may not be pure state. Then we have to have a general kind of formula. So that's why I want to introduce delta G of reaction. In this case, is product Gibbs energy minus reactant Gibbs energy. And product AB is pure state, so GAB naught, and then GA, GB naught. Then you can get this is same as this value, and which is typically explained in the textbook A plus BT term, because enthalpy minus entropy, T entropy term. And within given range of temperature, this value is almost constant. That's why we express typically A plus BT, but theoretically, this can be more complex than that. Okay, so when you're actually talking about MgO plus Al2O3 become NgAl2O4, okay? I mean, we know this Gibbs energy of reaction, and if you plot it with the temperature, depending on the chemical reaction you plot, you can have like a graph on the top, or a graph in the middle, or in the red line in the bottom, okay? So when you have the chemical reaction, delta G naught, delta G of reaction, by the way, in this case, is same as delta G naught of reaction. When it's always positive, it means you cannot make your product, yeah? Because your Gibbs energy of reaction is positive. So it means your reactant is stable. And then when you have the graph on the bottom, the curve in the bottom, it means your reaction Gibbs energy is always negative. It means you can always produce your product thermodynamically, okay? And sometimes we have something in the middle, so it means depending on the temperature, we may form, we may not form, okay? But this is all considering the pure standard state without the solution state, okay? So this value, you cannot change it. This is determined by the nature by itself. Okay, now let's add a little bit of solution. The first solution we can add is always gas phase. So for example, if you have A plus oxygen become A oxide, iron plus oxygen become iron oxide, something like this. Then now Gibbs energy of reaction equal to product minus reactant again. And the product is AB, let's say A oxide. Let's assume this is pure oxide without solution phase yet. And A, and then B, gas phase. And gas usually make always, gas can easily make a gas solution phase. For example, oxygen with a nitrogen as air, okay? Of course, you can make a pure oxygen, but depending on the pressure, total pressure, your Gibbs energy can be changed. Gibbs energy of the pure oxygen at standard state, it means at the 1 atm condition. But if you make it 100 atm, their Gibbs energy is changing from 1 atm condition. So how can you actually decide that? Gibbs energy of any gas species in solution or in the pure state is their standard Gibbs energy at 1 atm condition plus RT ln partial pressure. And partial pressure, of course, containing mole fraction times their total pressure. Okay, so that's why this Gibbs energy of this oxygen can be changed now depending on your environmental condition. So if you consider this one in this equation, you can sum up and then you can summarize this equation in this way, which containing now partial pressure of oxygen. Now we have the interesting game. In the previously, when I say everything is pure, solid become another solid, then nature just decide your Gibbs energy. So we cannot do. Either it goes forward or backward or in equilibrium state, both together. Okay. But now, by changing the oxygen partial pressure, you can control the chemical reaction. You can control, make it forward reaction or backward reaction. Okay. So for example, like this. So Gibbs energy here. And if you're considering only pure standard state Gibbs energy, let's say it's like this. But by changing your partial pressure, now you can bring it down or bring it up, whatever you like. And at the given temperature, if I want to know exactly the transition from iron oxygen become iron oxide, like that oxidation condition or reduction condition, we can just make this equation, delta G of reaction equal to 0, and that give you the answer for the how much partial pressure of oxygen I could need to actually control that to maintain that actual condition. And that's typically, we say actually kind of the oxygen partial pressure on that borderline. Yeah. And so when you consider more and more other gas species, we can just generalize this equation like this. Okay. So at least you understand difference. Delta G naught of reaction and delta G of reaction. And one of the most famous diagram about the oxidation of the metal is Ellingham diagram, of course. Ellingham diagram is collection of all the Gibbs energy of the standard Gibbs energy of reaction for the metal with 1 mole of oxygen become another metal oxide. That's the collection of the Gibbs energy here. Okay. And a lot of you, when you learn the thermodynamics, collective thermodynamics, probably you learn this actual graph to obtain what's the equilibrium oxygen partial pressure. Yeah. So for example, let's say here I have iron oxygen become iron oxide. At the given temperature here, if I want to know what's the oxygen partial pressure I need to make this one at equilibrium state, it means delta G of reaction equal to 0. Then you can point actually from here through the straight line through to that point, and you can read the sum of the partial pressure value here. That's the equilibrium. So that's basically graphical solution of the previous, mathematical solution. Okay. And it's a nice diagram, but you have to know that this Gibbs energy, this actually representation is very important. However, this is based on the everything, all the solid or liquid reactant, except for the oxygen, everything is pure standard state, no solution phase. And sometimes this actually give you the wrong the information about your chemical reaction. So for example, let's look at this one. So if you look at the bottom of this Ellingham diagram, there's the calcium oxide in the very bottom. Sorry, here. So here you can see the calcium oxide in the very bottom, and then you can have magnesium oxide just above. So if you look at this chemical reaction, CaO plus magnesium becomes Ca plus magnesium oxide. This delta G naught of reaction is always positive. So is this chemical reaction can happen or not? Not happen. Come on, not happen. Happen. I don't know. Yeah. This is reality about thermodynamics, So theoretically, if you assume everything here is pure standard state, it means if it is not making any solution phase, this reaction cannot go to the forward reaction. It's always in the backward reaction. So CaO is more stable than MgO. But in reality, if the calcium and the magnesium can start to make liquid solution at high temperature, and this temperature about 700 degrees, both can make actually liquid solution, then the dynamics can be changed. So when you say, okay, what's the equilibrium condition? You are not only looking for the delta G naught of reaction. You have to look at really delta G of reaction. This is the very important lesson for you. So we have to look, when you're talking about the reaction direction, delta G of reaction value is important. And delta G of reaction equal to delta G naught of reaction plus RT ln all the activity, all the partial pressure we learn. And I'm going to introduce that activity a little bit later. And so this is the equation we have to look at it. And then if the component, reactant or product is they are pure standard state, activity equal to 1. But if they are making solution phase, their activity may not be 1, less than 1 typically. And depending on that, this reaction can go forward reaction. So in reality, at 700 degrees Celsius, believe it or not, you can make up to about 10% of magnesium can dissolve to the calcium no, 10% of calcium, sorry, dissolve into the magnesium and driving this chemical reaction forward until the magnesium reached to the about 10%. And the calcium is reached to the 10% in the magnesium liquid. Okay, this is actually about $5 million patent in the magnesium industry, believe it or not. When this idea, in the magnesium industry, people want to make a pure magnesium, magnesium alloys containing calcium. It's having very good mechanical property. But when you introduce the metallic calcium, it always make actually calcium oxide around it. So it always introduce the oxide, which deteriorate actually their mechanical property. And this guy in Korea, he actually say, okay, accidentally, he put the calcium oxide on top of the magnesium liquid metal. And then he found out that calcium actually is going inside of magnesium metal and make a very, very high purity without oxide inclusion inside and magnesium calcium alloys. And he make a patent. And for the magnesium alloys and also additive for the aluminum alloys as well. And it's a huge patent. And when this actually technology was first patented, and when he introduced this one in the academic side, in the conference, nobody believed that. Ellingham diagram didn't say that. But this is the reason. You can actually do it. Then what's the activity? So when you make a solution phase, okay, because of the interaction between the species, now the chemical activity, the movement of this species for chemical reaction can be changed by your environment because of the interaction. And that's actually the activity we are talking about. So whenever you're actually looking for the solution phase, there are Gibbs energy in the solution phase can be determined by the pure Gibbs energy, their standard Gibbs energy, plus correction term. And that correction term is RT lone activity. Okay? And then when you say, okay, the Gibbs energy in I in solution, we say it's a partial Gibbs energy because it's part of the solution, partial Gibbs energy of I in the given solution. And classically, we explain that actually the Gibbs energy, activity as by dictating this kind of partial pressure. This is ideal. And so activity is expressed typically by the activity coefficient and the mole fraction. Of course, it is very, very difficult to find out activity coefficient. And most of the time, we have to do the experiment. And in the fact stage, we can actually have all the formula, which can allow you to actually get the activity coefficient by automatically. So you can actually do the equilibrium calculation. So depending on, as I told you, whether the species like each other or don't like each other, you can have different energy. And depending on that, you can have more attractive force. It means your activity coefficient is lower than your ideal condition. And then if you have repulsive force, your activity become higher than your ideal condition. That's actually presentation on that graph. So now, if you consider all these kinds of solid solution, liquid solution, and gas solution all simultaneously, then we can properly understand the chemical reaction of the complex reaction. So for example, if you have A and the B reacting together and then make a C and the D, okay? So Gibbs energy, their Gibbs energy is determined as expressed as delta G of reaction equal to all the partial Gibbs energy of product minus partial Gibbs energy of the reactant. Then if you express this one as a pure standard Gibbs energy and the activity, then you can collect it back in this actually equation here. And here, delta G naught of reaction, which is important actually factor, but you have additional correction term by the environment. How you actually set your environment. You can actually now switch this delta G naught, even positive, to make it negative or make it equilibrium state. Okay? That's why we're actually doing engineering. So let's go back to this example again. So if you are talking about pure standard state, this is always the CaO is more stable than MgO. So the Gibbs energy change for the reactant and product is more stable. Okay? But now, if I actually allowed this calcium and magnesium make a solution phase, now we can change the Gibbs energy of reactant and product actively, simultaneously. And then, depending on your environmental condition, you can have forward reaction or backward reaction. If you leave it for a long time to make it actually the lowest energy state, then you can achieve to the actually final equilibrium state as well. So this is most important message I want to give it to you. Thermodynamic delta G naught of reaction is determined by nature or by God. I don't believe that much God, but anyway, by nature. So you cannot change this value. But the God allow us to do something, and that's actually the environment. So we can actually put this, the reactant and product in different environment, and then we can actually force this the unfavorable chemical reaction become more favorable chemical reaction, and then make something for the fortune. Okay, that's the thermodynamics. And one example for steel making, for example, look at this one. So if we are adding ferrosilicon in the CaO and the liquid steel, then ferrosilicon is typically the weight is between slag and actually density slag and the steel. So it stays in middle in the beginning. Okay. Then iron oxide and silicon oxide is the less stable than CaO or Al2O3. So it should not make a chemical reaction. However, because this make a solution phase, that's why you have the calcium oxide even can be reduced by the silicon to make calcium metal and silicon oxide. And this calcium is going to this liquid metal in the middle, and then it can sinking down, and then make calcium is available inside of your liquid metal too. That's possible. And this is basically what's happening in the ladle furnace process when you add the ferrosilicon, and there's sometimes calcium oxide forming, calcium sulfide forming for the dephosphorylation, deoxidation and desulfurization. That's how actually it's really happening. Any process, you have to look at in this way. Okay, now, when you know the Gibbs energy function for the solution phase, so for example, solution AB, their Gibbs energy is simply the mechanical mixing of this partial Gibbs energy term, then you can rearrange this one as a standard Gibbs energy with that extra term, that's activity term. Okay, so if I know the activity change depending on temperature and the composition, then I can draw the Gibbs energy in any composition, any temperature domain. Okay, then, so for example, let's look at this one, T2 at T2 temperature. Let's assume I have alpha phase, beta phase, and liquid phase. If I know the Gibbs energy of this one, as it is, with the composition, then I can draw the Gibbs energy like this. And then at each composition here, at the given temperature, we want to know what's the equilibrium, phase. Okay, the chemical reaction. Is it going to, which phase is more stable? Yeah. So here at the bottom here, you can see that alpha phase is more stable, and here liquid phase and beta phase. And when you see the here, because of the cotangent line, so we can actually have the minimum Gibbs energy by combining of the alpha and the liquid phase, which actually make a lower energy than pure alpha or pure liquid. So that's why we can have two-phase region here. Okay, so if we're representing all this the equilibrium composition into the diagram, then we can make phase diagram. Okay, so this is the idea about the computational package to generate their phase diagram. So in the fact set, you can draw up to about 7-8 components of the phase diagram, and all this one is actually, all that actual calculation is done by behind like this kind of the idea. Okay. So then let's talk about a little bit more, calculation scheme of the equilibrium state in the fact stage, for example. So when you're actually talking about A, B mixing together at the input at the given final and final temperature and final pressure condition, we can have the numerous possible phase by just combining these two phases. And of course, when you learn the thermodynamics in the undergraduate level or even graduate level, when you take an exam, your professor always give you okay, you have to use this equation. So this is equation. Then it's easy. Then we can just take the actual Gibbs energy from the literature and activity data somehow in the literature, and we can do that, and then we can find the delta G equal to 0, then we can find what's the equilibrium state, what's the composition, and etc. It's easy. But if you are supervisor or you actually teacher, don't give this equation, then what will happen? Misery. It's very difficult because we have so many possible combinations to have mass balance of this reaction input, and so many possible actually the output based on the mass balance. And which one have the stable state? And theoretically, when you have the lowest energy state in terms of Gibbs energy under the mass balance condition, that's the most stable state, yeah, that everyone knows. And so what actually computational thermodynamic software is doing, they have special algorithm to check all the possible, phases, combination like this. And each of these one, they actually somehow making the very fast algorithm to check how does Gibbs energy change. And then they found what's the minimum Gibbs energy state. And so, okay, so this is the equilibrium state for you actually when for your input at the given final temperature and final, the pressure condition. So that's how it is working. Okay. So you don't have to remember all this one because now there's software like the FactSage is available. If you don't have it, buy it. If you don't have it, you can contact me, of course. Yeah. And I can give you free consulting. Okay, so there's the software like this. There's many different software, but one of the software most, famous in the refractory and steel making is FactSage, which was developed from 1976, and it have huge thermodynamic database. And that thermodynamic database basically containing all the partial Gibbs energy equation for all the different kinds of phases, depending on temperature and the composition. Of course, inside is more complex, but you can assume in that way. Okay. So what kind of database we have already for the refractory industry, for example? So for example, steel making and non-ferrous and cement industry, we always talking about the slag. And so CaO, MgO, Al2O, SiO2, whatever. And then all different kinds of refractory material, mag carbon refractory, alumina spinel refractory, and chromate and all kinds of things, So all this one is more or less available already in our database, including very recent one. It is not available yet. Chromium 6+, which might be also important for the chromium oxide containing material, especially in the high oxygen partial pressure or sodium oxide, alkali oxide condition. And we recently developed huge database for the layers oxide. I'll show you a little bit about this one later. And then also oxyhydroxide database. And for example, Jung just show actually some kind of explosion when you add some, the water and then, depending on chemical reaction. So we can now calculate what kind of oxyhydroxide can be formed under different kinds of the, total pressure condition, those kinds of things. And then also we have for the glass or biomass combustion and coal combustion, we have all these kinds of the alkali oxide together with the sulfide, sulfate, and etc. So it's not perfect, but it can give you a lot of the idea. It have the wide range of the application already. Good for the wide range of application. Sorry. And then because this is not only for the refractory, I say ultra high temperature ceramic material. I think from my point of view, ultra high temperature ceramic material is also refractory material under that extreme environment. Okay, so for them, they are typically using carbide, nitride, and then all this high temperature material. And we also have those kinds of database. And then also this carbide, nitride, and also the boride, when it goes to the extremely high temperature under the oxidation condition, now you have everything is oxidized. So it means you're back to the oxide again. So we have to know all these oxide actually components simultaneously. We are developing a lot of this kind of the database for this industry in this day. And so I'll share some of this actually results with you too. So this is the example I want to show you. So how to utilize this kind of computational technique to understanding all this kind of thing. Refractory corrosion by the slag and corrosion by the metal, liquid metal, and then corrosion by the gas species. And some of them is UHTC kind of application. And so I hope actually you can look at some of this UHTC, and it's very interesting. And there's a lot of window for our refractory people can invade and helping them, not like attacking them, helping them to design the new the ceramic material there. So let's look at the very classical ternary phase diagram, CaO, MgO, SiO2 ternary system. And this is drawn by FactSage at 1600 degrees Celsius. So I know, a lot of people most probably know how to read the ternary phase diagram. But if you don't know, let me just introduce you one actually, how to read it. So for example, let's assume at this composition here. And then if you look at how to read the composition here, that's most important. So if you look at here, this is pure CaO, pure SiO2. So it's SiO2 content is changing 10, 20, 30, 40. So it means here, it's about 50% of SiO2, okay? And then now if you look at this axis, the MgO content is changing from 0, 10, 20, 30, and etc. So it means at this point, you have about 10% of MgO, and the rest of them would be CaO concentration. Okay, so that's how we read it. And if you go to the quaternary and the quinary system, and if you know the certain amount of the constant value, you can use the same idea and then read actually your diagram. So for example, at this actually composition, we see that this is only single liquid phase area. And here you can have liquid plus MgO two-phase region, of course. And the all dotted line show you the tie line of the two phases. Okay, so now this line here is the Ca2 SiO4 saturation because it's connecting with the Ca2 SiO4 plus liquid. And this is the liquid composition saturated with the MgO. Okay, so for example, if you have the slag like CaO SiO2 50-50, and then if you put this one into the MgO refractory, then magnesium oxide can be dissolved continuously until it reaches to this boundary liquid composition. So this is MgO solubility in your slag. And so in order to design actually your slag properly to minimize your MgO refractory dissolution, then you have to take this composition for your slag composition. Of course, depending on your refining capacity of your slag for steel making and MgO together, the best one is this dicalcium silicate and MgO co-saturation point. And there's you can change something also, but at least we can run all these kinds of MgO saturation curve from the phase diagram. And depending on the CaO MgO, actually the ratio, you can have different amount of MgO saturation. So this kind of ternary phase diagram give you the idea about how to control, how much MgO dissolution I can expect from my slag. And let's move to the quaternary. So this is quaternary phase diagram. So CaO MgO SiO2 with 15% of Al2O3, we fixed the alumina amount, and then at 1600 degrees Celsius again. So here you can see wide range of liquid area here, and this is MgO saturation line. Okay, so this is the border. And again, CaO Al2O3 MgO with 5% of the SiO2. Here, this is MgO saturation line. Why we don't have the tie line? Because tie line is only working in the ternary system with a specific actually domain, but here the tie line is not on this plane actually, so that's why we cannot plot tie line. Okay. And now let's move on to the MgO dissolution in the CaO FeO SiO2 slag, the so-called BOF, the basic oxygen furnace. So this BOF is very important process in the steel making. So you have the high amount of carbon produced still from the blast furnace, and carbon is about 4%. So we want to reduce the carbon content. So we are injecting the oxygen, and while we are injecting the oxygen, carbon is actually going away as a CO gas, but iron is start to actually burning as a FeO. So the composition of the slag on this furnace is changing from this point to all the way travel back to this point again, same composition. Okay, and of course, with actually that about 15 or 20 minutes of time, the temperature of the furnace is changing from 1350 to almost 1700 degrees Celsius. So this actually slag traveling around this actually different temperature as well. And then if you draw the phase diagram at for example, 1650, that's just some more or less final condition at 1650. And we are adding typically about 5% of MgO into our slag to prevent MgO the MgO dissolution of refractory MgO in this process. And then if you look at actually what's the MgO saturation line here is this line. And this is not strictly MgO saturation line because MgO and in this slag, CaO FeO SiO2 slag, MgO and FeO make a fully solid solution. So this is MgO and FeO solid solution. So typically when you examine your MgO refractory after BOF operation, if you take it out on the interface actually side, you can see a lot of FeO is dissolved in the MgO refractory, and because it makes a solid solution. And now this is another example for with the alumina and the CaF2. So in the CaO SiO2 with the MgO. So this is the rectangular diagram of the CaO MgO SiO2. Here SiO2 concentration. This is MgO concentration. So this is C2S saturation I showed you before in the ternary triangle diagram, and this is MgO saturation. So this is the point we want to keep our slag to maximize refining capacity plus minimize refractory dissolution. And this composition can be widely changing depending on your slag composition. So for example, this is starting point, zero alumina, zero CaF2. But if you're adding about 10% CaF2, it moves here. If you're adding 20%, 15%, 20%. And with the alumina addition, you can have also wide range of the change of this composition. So if you don't know this composition before, and if you just designed your slag without any knowledge like this, then your refractory will be heavily damaged during the operation like this. So the phase diagram is very important. And this is another example I did. I made with my colleague in the Almatis, yeah. And so they are producing the porous plug with a high alumina. So here they are conventional plug containing little bit of CaO and then alumina and MgO, like this composition. And then they install this actually and made of this one, they make actually porous plug. And this porous plug is working as oxygen kind of the lens going to actually this porous plug and then make oxidation of this bubbling inside this one. And then while actually they are doing this one, they found out that at the end of the process, this oxygen start to make chemical reaction with the remaining slag, which is typically Fe2O3, we can assume in that way, and then make this Fe2O3 and this porous plug start making chemical reaction. Okay, so they want to know, okay, whether this CaO addition have some impact or not. So we draw the phase diagram, like here is this refractory material in the x-axis on this corner, and on this corner we have Fe2O3. And then you can draw the phase diagram in air, and then you can see that, okay, this line show you, this is the lowest temperature line for the slag formation. So above, you can have always liquid phase, okay? So with the CaO, without CaO. Without CaO have a much higher melting temperature. So why? Because CaO going to the slag and make actually slag become more stable, so you actually reducing its melting temperature. That's what is happening. So it can give you the idea how to actually change this kind of recipe for the refractory material. So this is another one, lithium ore rotary kiln process. And a lot of people, especially if you want to make a lithium battery, we have to extract the lithium from we have to have the pure lithium or lithium hydroxide or lithium carbonate as a starting material. And they're actually producing from the typically ore, like a spodumene ore, or produced from the brine, LiCl, from the brine actually liquid. So this is the spodumene ore process. So they want to actually transform the structure from alpha, beta, gamma. There's three actually phase transition, and they are natural actually the ore crystal structure is too dense, so you cannot actually making actually chemical reaction to extract out the lithium. So that's why they wanna do kind of the transformation of this material to the very dense one to the less dense one for the accelerating the extraction process. So they are using this rotary kiln at around 1200 degrees Celsius for acceleration of this phase transformation. And one of my sponsors stupidly take the MgO without any my advice. And then they say that, okay, entire rotary kiln refractory was, making chemical reaction with the lithium ore. And so we did the calculation for them. Here, this is spodumene, LiAlSi2O6, and this is MgO. And you never seen this kind of phase diagram before. But here, this red line showing you the minimum temperature for the slag formation. So if you are doing 1200 degree operation, here you can make a huge amount of liquid slag, which can stock inside of your rotary kiln and make damage more and more, and then eventually it failed. So they changed based on this one, they changed their refractory. Okay, so this kind of thing. And now let's look at the reaction with the liquid metal. So a lot of people thinking there's probably almost no reaction with the liquid metal and the refractory, but it's depending on the case by case. And so, for example, this is the TWIP steel production. So 18% of manganese and 1.5% of aluminum with 0.5% of carbon. That's typical TWIP steel composition. And then they want to use the mag chromate refractory, MgCr2O4, typically known as very stable refractory. But if you're actually doing this chemical reaction, so now MgCr2O4, is it really stable under this condition or not? And it is not. In fact, if you actually look at here, this is pure MgO, and this is the MgCr2O4. So I did thermodynamic calculation, assuming 100 gram of TWIP steel with 100 gram of refractory, but x-axis here is changing of the X composition here. So here is pure MgO, and here is pure MgCr2O4 at the 1600 degrees Celsius, and I plot what kind of phase can be formed. So of course, there's the 100 gram of liquid steel, and then you can see that different kinds of phase can be formed depending on your composition thermodynamically. But if you look at inside of liquid metal, you can see huge amount of chromium pickup, and this is coming from the MgCr2O4, of course, and then huge decreasing of the manganese, zero amount of aluminum, because MgAl2O4 is more stable than MgCl2O4 in chemistry, in the Gibbs energy point of view. And then also MnCl2O4 can be also one of the stable phase. So that's why, because of this interaction reaction happening. And then eventually you can see that your refractory, for example, MgCl2O4 can be changed their composition because of this chemical reaction. So they see huge degradation of this kind of refractory. And of course, now if you're doing MgAl2O4, it's very stable, very good. And you can actually prove that by the thermodynamic calculation. Now let's move on to the refractory and the gas reaction. So a lot of people talking about hydrogen usage in this day. So hydrogen is very important. So left side, you can see that MgO and hydrogen chemical reaction with the temperature, just pure MgO with a pure hydrogen at 1 atm condition. And you can see what kind of gas species can be formed theoretically in the thermodynamic condition. So here, almost pure H2 as it is in the log scale here. But you can see that magnesium partial pressure and H2O partial pressure is picking up very quickly with the increasing of temperature. So theoretically, if you see about 10 to the minus 4 partial pressure of oxygen, it means it's enough to see the actual degradation already. Okay. So here about the 13, 14 degree, if you actually put the magnesium oxide under hydrogen condition about 13 or 14 degree, you can start to see some kind of magnesium vapor start forming. That's what is happening really. Okay. And now how about if you are changing H2 and H2O gas simultaneously? Because if you are using H2 for something, it make a high, some chemical reaction always probably make H2O. So we have to look at both these H2, H2O conditions simultaneously sometime. So with the magnesium here, H2 condition here, and this is H2O condition. Under the H2O condition, as Jung also said, MgOH2 can be formed at low temperature as a solid state, in the high temperature as a gas phase. But this is not enough to make a pure MgH2 OH2, but you can see about 10 to the minus 5 partial pressure of the MgOH2 can be formed. But of course, if you go into the higher temperature, you can start to see this will going up, then you can start to actually even have degradation of MgO refractory by the H2O actually. That's possible. And now this is calcium phosphate. Calcium phosphate is used sometimes for the bonding material in the some refractory. And if you actually put this one in H2O condition, also it have the problem. So calcium phosphate, P2O5, is not very stable phase. So if you actually put this one in the H2 condition, it can evaporate P2O3 gas phases. So you can see a lot of P2O3 gas phase formation here, even at 12 degrees Celsius. And now if you are putting this one with alumina, with actually that bonding material on the H2H2O condition, about 50-50 condition, you can even see that now at around 1000 degrees Celsius, you can start to see some calcium phosphate hydroxide formation as well. And then of course, if you are increasing this at the 0.5 condition with the increasing of temperature, you can see all kinds of the calcium phosphate P2O5 or PO actually gas phase formation too. So this is the degradation of your bond material. Then it means your refractory will be, the weakness, the strength will be gone. So actually have the degradation automatically. And now this is the phase diagram for the very high pressure of H2O environment. So for example, this is CaOAl2O3 binary system at 100 atm with a partial pressure. So H2O 100 atm. So see here, instead of CaOAl2O3 some other compound, you can start to see that here some hydroxide formation. And then it changes it, and then it can form another hydroxide. And above this temperature, you don't have any hydroxide. So we can do this kind of calculation in any pressure up to the several gigapascal now. And so we can actually look at what kind of the hydroxide can form depending on temperature. And this is another example for those kinds of ternary phase diagram calculation. So I have only very short minute. Okay. So let me just show you very quickly about the ultra high temperature ceramic application. So this is the EBC or UHTC kind of application. So EBC material is environmental barrier coating, and which is typically used is the rare earth silicate phases, which is used especially for against this kind of, the turbine material. But unfortunately, in this turbine, the engine is actually performed in the height, in the sky. There's always dust like CaO, MgO, Al2O, SL2 dust. If you go to the volcanic region, there's also additional FeO dust, and then that form liquid slag at this about 1400 degrees Celsius, and that can damage this kind of refractory material on the turbine, at the coating, EBC coating, sorry. So we made a special database now for the layers oxide with all these kinds of the important slag actual component. So this is the one of the example. So YB2 Si207 is one of typical EBC coating material. And then on the bottom, they have SiO2 coating. So these two have the almost no chemical reaction because here YB2 SiO7 and SiO2. So there's no new phase in the middle. So it's stable at this temperature. And their melting temperature is almost about 1850. So it's quite stable up to this temperature range. And they don't have any phase transformation with the temperature compared to the other actually layers disilicate which have phase transformation. So that's why they use the ytterbium silicate material here. But when you actually put this ytterbium silicate material under this kind of dust condition, and people try to do the kind of refractory type of the experiment, refractory slag experiment like this. So here, this one, and they put all these kind of CAMAS kind of the imitate of that dust material, and then increase temperature 13 to the 1400 degree, and they did experiment. And they found there's a different kind of phase formation. So this is kind of phase diagram we can calculate now. So we have ytterbium silicate, YbSi205, reacting with the CMAS, that's specific composition. And then you see all this red line, again, showing you the minimum temperature for the slag formation. So if you're operating this one above the 1250, then you can start to have the liquid phase formation by forming some solid phase like garnet and apatite phase, and et cetera, et cetera. So by knowing this phase diagram and by using thermodynamic database, we can change some recipe of this kind of the coating material to get more resistance against this kind of the environment in the extreme environment. Okay, and there's many other examples. You can look at it. Probably I don't want to spend too much time. Okay, and if you have questions, you can come back to me. So this is all the silicon oxide and zirconium boron oxide and hafnium boron oxide oxidation and evaporation and the phase transformation reaction, all explained roughly here. If you have any question, you can come back to me. Okay, so phase diagram is very important. Thermodynamics is very important. And if you have the tool like FactSage, you can do the very simple actual calculation to understand your chemistry. If you don't know, you can actually contact me. I can help you, no problem. Okay, with that, thanks for all your attention. Thank you very much.